What if the four fundamental forces that run our entire universe, everything from the inside of an atom to the dance of galaxies, aren't four separate rules at all? What if it's just one single rule seen from four different angles? Well, a brand new paper is suggesting exactly that. It claims the answer's been hiding in plain sight, and get this, it all just comes down to a matter of perspective. Let's dive in. So, for more than 100 years, physics has been wrestling with this enormous puzzle. Just look at the four fundamental forces. Their strengths and ranges are all over the place. You've got gravity, right? It holds entire galaxies together, but it's just unbelievably, bafflingly weak. And then you have the strong and weak nuclear forces. They're absolute titans, but they only work inside the ridiculously tiny space of an atom's nucleus. They don't even seem to be playing the same game. It's like having four totally different rulebooks for how reality works. And that, of course, leads us to the biggest question, the holy grail of modern physics. Are these forces really separate entities, or is there one single unified principle hiding underneath it all? A new and pretty radical theory is saying yes, there is. And the secret is all about perspective. Okay, so first, let's just take a moment to really appreciate the puzzle itself. This quest to unify the forces, to find where they all come from, is one of the biggest challenges in all of science. And it's precisely because they seem so incredibly different from one another. Now, what's so fascinating about this new approach is that it basically flips the whole question on its head. Instead of just asking how these forces work, it asks a much deeper question. Why? Why do they have these exact properties? And the theory suggests the answer isn't some new particle or a hidden dimension, but a fundamental dial in the universe that actually sets the rules. So this brings us to the core idea of the theory, and honestly, it's a pretty profound one. What if the differences that we measure between the forces aren't actually fundamental properties of the universe at all? What if they're just illusions, created by the very scale at which we happen to be looking? The theory introduces this concept called the absolute structural scale, which they label with the letter L. Now, the easiest way to think about L is as the pixel size of reality. Just like a photo on your screen is made of tiny pixels, this theory suggests that at any given scale, the universe has a fundamental resolution. And this pixel size, this L, is the master dial that determines how strong a force appears to us. And the rule it proposes is just beautifully simple. The strength of any force is basically the inverse of this structural scale. So here's the key takeaway. A smaller L, meaning a finer, more detailed pixel size, gives you a stronger force. A larger L, a coarser view, gives you a weaker force. It's all about the granularity of your perspective. Okay, so if L is the master dial, what's turning it? Well, the theory proposes this really fascinating mechanism called the 12-to-1 cosmic cycle. You can think of it almost like a master algorithm for how the universe's structure simplifies itself and then reemerges as you zoom in or out. So here's how it's supposed to work. At a really, really fine scale, reality is described as having 12 distinct structural parts. But as you start to zoom out, your perspective gets coarser, and those 12 parts begin to blend together. They coalesce. Eventually, you zoom out so far that you just can't tell the 12 parts apart anymore. To you, they just look like one single simple thing. But this cycle doesn't end there. If you zoom out even further, new 12-part structures start to emerge at this new, larger scale, and the whole cycle is ready to begin again. And the paper itself puts it perfectly with this quote. This is so important. This 12-to-1 transition isn't something physically happening to the object. The 12 parts are still there. It's just a change in what an observer can see. It's a limit that's imposed by our own resolution. If you can't see the individual pixels on a screen, all you see is a smooth image. Same idea. So how in the world does all this solve our original puzzle of the four forces? Well, this is where these ideas of scale and coalescence really start to pay off, giving us a single, unified framework to explain all four of them. All right, let's look at gravity and electromagnetism. The theory says they're not different forces at all. They're the exact same underlying geometry. The only difference is the scale we're viewing them at. Gravity is what we see at a huge structural scale, where those 12 parts are so deeply coalesced that they look like one, resulting in a very weak force. Electromagnetism, it's the same geometry, just viewed at a much smaller scale, where things are less coalesced, which results in a much, much stronger force. Okay, so what about those super powerful but short-ranged nuclear forces? Well, the theory claims they are the same fundamental geometry too, but they're operating in a really constrained space. Imagine a force they can't spread out in all three dimensions, but instead is basically trapped, confined to a line or a flat plane. That's what reduced dimensional means. Because they're stuck inside particles like protons and neutrons, their influence just can't escape very far, which is why their range is so incredibly short.
And here it is, the unified picture. The entire messy zoo of forces suddenly gets organized, and it's classified using just two simple ideas: the dimensionality it's working in, either 3D or reduced, and the degree of that structural coalescence. All of a sudden, the four separate rulebooks, they merge into one single coherent story. It's a pretty stunningly simple and powerful idea.
Now, this all sounds absolutely incredible, maybe a little too incredible. But is it actual science, or is it just a really neat philosophical idea? Well, the true test of any scientific theory is whether you can try to break it. So let's look at exactly how we could try to prove this one wrong. So just as a quick reminder, for any idea to be truly scientific, it has to be falsifiable. That means it has to make real, concrete predictions about the world that we can actually go out and test. And if those predictions turn out to be wrong, then the theory is wrong. Simple as that. This paper makes a couple of very specific testable claims. Prediction number one is all about that structural scale, L. The theory says that if we go out and measure a bunch of different physical systems and then work backwards to figure out their underlying L value, we shouldn't find a smooth, continuous range of values. No. Instead, they should all clump together into these distinct bands, with each band corresponding to a different stage of that 12-to-1 cycle. So if we look at the data and find a perfectly smooth distribution of scales, the theory is broken. The second key prediction is something they call a decoupling, and it's actually pretty straightforward. The theory says that while the strength of a force depends entirely on L, the speed it propagates at, like the speed of light, is constant and completely independent of L. This separation is absolutely critical. If experiments were to ever find any kind of systematic link between how strong a force is and how fast it travels, that would falsify the theory. And all of this leaves us with a final, really profound question. This theory is proposing a universe that isn't built on four random, arbitrary rules, but on a hidden, repeating structural code. A universe where the fundamental laws of physics aren't absolute truths, but are simply a matter of perspective, a matter of how closely you're looking. What do you think?